Quiz2.
This meeting is being publicly streamed.
Yeah, we are going to start the. Today we will discuss the week 7 and week 8 contain. Uh, okay, so let's start with eigenvalues. So in week 7 we studied eigenvalues, eigenvectors, how to calculate eigenvectors corresponding to each eigenvalue, and then we studied in the week 8 the uh, diagonalizability of an linear operator. Okay, so let me start with the definition of eigenvalues and eigenvector. So eigenvalue of an matrix. So we find so eigenvalue of a matrix is called so given so let A be n cross n matrix. So the lambda real real or complex or in particular lambda in F is called an eigenvalue of A if there exists non-zero vector V in your vectors V in Rn V in Fn such that AV is equal to lambda. Alright. Or in particular, you can define it for the linear operator, and then that becomes equivalent when you have when you represent your the linear operator in terms of uh, so let T be an linear operator from Fn to Fm and A be a matrix representation of T with respect to canonical basis. So then let me just yeah. Okay. So then TV is same as AV, which is equal to lambda V. And the vector V is called the eigenvector. Right? Called an eigenvector to lambda. Alright. So this is the definition of the eigenvalue. In particular, using this equation, we can how do we find the eigenvalue? So to find the eigenvalue, we look at this uh, AV minus lambda IV is equal to 0. That means because this this defines an operator which is A minus lambda I that acts on B and gives you 0. So this means this operator must be of determinant 0. So that is what we use to find out the value of lambda. Okay. So this will give you some polynomial in terms of lambda, and then the roots of that polynomial are called the eigenvalues. So roots of polynomial are called the eigenvalues. All right. So now in this question, we need to find out the which of the following is an eigenvector for the corresponding of the A corresponding to eigenvalue A. So we have already given an eigenvalue which is lambda equal to 1. So now we need to find out the eigenvector to that. And how do we find eigenvector? So for that, we need to find out the null space, basis of null space of a minus lambda I, which is in this case lambda is equal to 1. So it is nothing but basis of a minus I, which is null space of what is a minus I? 1, 1, 2, 1, 2, 3, 1, 1, 1, 0. Right. Now, in order to find out the basis of a matrix, what do? We perform the we need to convert it to row echelon echelon form. Do reduce row echelon form, and then we will find out the number of independent variables, and we express dependent variable in terms of independent variables. Right. So let's do that. So let me first start with R1. So R1 is 1, 2, 1. So let's first subtract this, and R3 minus R1. This will lead you 1, 2, 1, 0, minus 1, minus 1, 0, minus 1, minus 1. And you can see that second and third row are same. So you can add them or you can subtract them each and them. So now R2, R3 minus R2 will lead you to this, and you multiply R2 by minus 1 later. So I'm doing that. I'm doing both of the operation together. So you will end up with this, and then I perform the operation R2 minus 1. So I will get rid of this minus sign, and then I can further reduce to this. But what is the independent variable in this case? Can you tell?
Z.
Z is the independent variable, right? Now, so you can express everything in terms of Z. So, so if you express everything in terms of Z, so x is equal to minus 2y. So first, let me express y in terms of Z. So y is equal to z. Sorry, minus z, right? And x plus 2y plus z is equal to 0. That implies that x is equal to z. All right. So what will be the vector now? So the eigenvector will have this. So null space of a minus I is z minus z and z. Z is in R. So then it will be, the eigenvector would be 1 times this. Right? So this will be my eigenvector. So what is my eigenvector? Eigenvector is 1 minus 1 corresponding to lambda equal to 1 for this matrix. Okay. So this is how you find out the eigenvector corresponding to a given eigenvalue. You need to compute the null space of the matrix. Now, so we also saw some of the properties of eigenvalues in week 8. What were those properties? That you can convert any linear operator. So not every linear operator is diagonalizable, that we saw, right? So but you can always find out a basis, okay, such that the matrix representation with respect to that basis gives you an upper triangular matrix. Okay, so once you get an upper triangular matrix, you can say that the determinant, you can prove that determinant of a matrix, okay, determinant of a matrix is equal to the product of eigenvalues, and trace of A is sum of eigenvalues. Okay, this is what we saw in week 8. This is from week 8. Okay. So using this, now we want to solve this question. This question says let A be this, and then if the eigenvalues are that, find the value of k squared. So you just need to calculate the determinant of A. So if you calculate the determinant, what will you get? Let me expand the basis with respect to the row, third row or first row, whatever row is suitable. Let's expand with respect to this first row. So you'll get minus 1 times 1 minus k square minus k, then it will be minus k is equal to 0, right? Now, sorry, not equal to 0, sorry. So is equal to, this would be minus 1 plus k square plus k square. So that will give you 2k square minus 1, right? Now, because the eigenvalues are going to be minus 3, 1, minus 1, and 1, so what will be the determinant of A? Because it's a product of eigenvalues, it will be 3, right? Now, equate 3 with this, so what will you get? You will get k square is equal to 2. All right. So we use this property that product of eigenvalues is nothing but the determinant of a matrix. Okay. So when you have an eigenvalue, so given a matrix A, you can have an eigenvalue. So for A n cross n, uh, the this is going to be a polynomial of lambda. Now degree of this polynomial, sorry, yeah, so it's going to be polynomial, and the degree can maximum be maximum n, but that's not the point. The point is that it will have some geometric multiplicity and algebraic multiplicity. So what does it mean? So let's say your p lambda looks like x minus a to the power of n1, x minus b to the power of n2, and x minus c to the power of some n3. Okay, now suppose this is your p lambda. Then what is the, so what are the eigenvalues in this case? The eigenvalues would be a, b, c. Now, what would be the algebraic multiplicity of each eigenvalue? So, let's say for A, what would the algebraic multiplicity? Anyone?
1.
For A, what would be the algebraic multiplicity of A?
1, sir.
N1.
Yes, N1. For B, it would be N2. For C, it will be N3. All right. Now, in order to find out the algebraic geometric multiplicity, you need to find out. So, what will be the geometric multiplicity of A? What is by definition? What it would be?
Less than equal to a N1.
No, geometric multiplicity will be equal to nullity of A minus A I. Okay, nullity of this operator. Okay. Similarly, so that could be anything, but it has to be smaller than the algebraic multiplicity. It cannot be larger than algebraic multiplicity. Okay. So there are the two relations that we need to know. So first thing is this. This is the definition of algebraic multiplicity, and the second is that geometric multiplicity of an eigenvalue is smaller than algebraic multiplicity. All right. So now, for example, in this question, let's take this question. So consider 5 cross 5 matrix such that the nullity of A is 2. Which of the following options is or are true? So, so call them A, B, C, D, and now you guys tell me what are the correct options.
A option is correct.
Option A.
Yes, sir. B can't be correct, and
Okay. A is correct. Okay. B can't be correct. Okay, why?
Because we already have two nullity. So rank max could be 3.
Yes, exactly.
I think the C option would be correct.
C would be correct. Why do you say think so?
Because we have a nullity too, and GM is dimension of nullity.
Yes, not dimension of nullity. Nullity itself is dimension. Nullity is a number. Dimension of null space of A minus 0 I, which would be null space of A. Okay. So this will be wrong because nullity is 2. So what is the nullity of eigenvalue 2? Because it has nullity, because the matrix has nullity, non-zero nullity. That means the dimension of null space of A is non-zero. That means what does this mean? This means that A times V is equal to 0. Okay, so there exists some non-zero vector such that AB is equal to 0. All right, that is what the case is. So when you have this, that means what? Uh, yeah, so that means you can think of this as 0 times V. Okay, you can think of it as like 0 times V. So 0 becomes an eigenvalue of A. All right, so that's why the first option is correct. Now, because of the rank nullity theorem, second option can't be correct because rank of A plus nullity of A is equal to 5. Okay, the number of columns that is equal to 5. But in this case, nullity is given to be 2, so rank is exactly 3. So rank cannot be 5, so that is the wrong answer. Now, what is the geometric multiplicity of lambda equal to 0? So what is the geometric multiplicity in particular? So geometric multiplicity is equal to dimension of null space of A minus lambda I, right? In this case, lambda is 0. So let's plug 0 over here. So what you will get, 0 times identity will give you 0 vector, 0 matrix. So this is A minus 0. A minus 0 is again 0. So it is just A. So it is equal to dimension of geometric multiplicity of 0 is equal to dimension of null space of A. That means, which is nothing but same as nullity of A. Now, what is the nullity of A? It is 2. So geometric multiplicity is exactly equal to 2. So that's why C is 2, D is 1. Okay. All right. So now let's look at this question. So what does this question says? Let me. Yeah. So this question says that consider the matrix. The eigenvector corresponding to eigenvalue belongs to which of the following spaces? Okay. So I will give you a few minutes to think about this, and then I will ask what should be the correct answer.
So, third row.
Third,
Third row.
null space of A.
Oh,
Anyone?
so they are asking the eigenvector, right?
Yeah. Eigenvector belongs to which of the following space?
Row space of A.
Row space of A. Okay, that is correct. But is there are two options correct? What is the second option that is correct? Okay, so we can think of an eigenvalue. So sorry, the eigenvector. So let's say AV is equal to lambda times B, right? So what does this mean? You can think of, let's say you have a 3 cross 3 matrix. So you can write A as C1, C2, C3. Okay, and you can write V as, let's say, X, Y, Z is equal to some lambda times X, Y, Z. Okay, if you take, so now what you can say that eigenvector lambda xyz is your eigenvector. So you can take lambda to this side, let's say 1 over 0. Yeah,
Sir, I think
because
the left null space of it.
no, not the null space. It is null space when eigenvalue is 0, right?
Okay, sir.
The eigenvalue is not 0. So because lambda is non-zero, you can take lambda to be this side. Okay, now what you can think of? So x by z becomes x times c1, x by lambda 1, y times c2, z by lambda times c3. That is equal to x by z. So what does it say? That x by z belongs to the column space of A, right? So that means eigenvector belongs to the column space of A. Okay. Now, can we do the same for row space? Let's see. So you have, and then you have x, y, z is equal to this. Okay, now let's see what's the determinant of this matrix. Is it a non-zero matrix? That means is it uh, right? Okay, that will not help us. So
I have a feeling it will be just the column space, I think.
no, the row space is also the correct answer. Uh, yeah, Ananya, why do you think that it would be null row space? Can you?
Sir, because if we do this A transpose, or
Yeah,
like if we even just
so the eigenvalue remains same. Yes,
yes, sir. So then we will get this 0, 0, 1 and the one eigenvalue.
right. So this is uh, yeah. So what is this matrix? So this is what is A transpose of this matrix? It is 2, 0, 0, and then 1, 2, 3, and then 0, 0, 1. But this is a different matrix, right? The eigenvalue will remain same. It will has one as eigenvalue, but uh, yeah. What was your argument? Can you complete your argument, Ananya? I've taken the transpose.
So now in the third column, we can say that here we have eigenvalue from the properties we have studied.
Yeah, you can say that, but this is not. This is not A. Okay. Let me. So if you multiply 0, 0, 1, so what will you get? Okay, so let's calculate the the eigenvector for this. So this
So how did you say that column space of it?
yeah, column space I explained, right? I just explained column space.
Sir, but that was A transpose, right?
No, that was not A transpose. That was A only.
Okay, sir.
Yeah. So let's look at the eigenvector. So it is 1, 0, 0. It is 1, 1, 3, 0, 0, 0. Right. This would be the A minus I. And now if you look at the null space of this, what will be the null space? It will be just yeah. It will be 1, 0, 0. 0, 1, 3, 0, 0, 0, null space of this thing. Okay, that means y plus 3z is equal to 0, x is equal to 0. Alright, this would imply that y is equal to minus 3z and x is 0. So the general vector will look like 0, minus 3, 1. Okay, so this is your eigenvector. Right. So now you need to say this is equal to a times 2, 0, 0, b times 1, 2, 3, c times 0, 0, 1. Okay. So let's check. So, we'll get 2a plus b equal to 0, and then 2b plus 2b equal to minus 3, and then 3b plus c is equal to 1. Right. So if you solve this, you will get b is equal to minus 2 by 3 and minus 9 by 2 plus c is equal to 1. This would imply that c is equal to 1 plus right. So c is equal to what? 1 plus 9 by 2. So it is a solution, and then a is also equal to plus 3 by 4. Right. So that means it has a non-trivial solution. So you can express the eigenvector in terms of the row space also. So eigenvector also belongs to the row space also. All right. Yeah. Now, yeah, clearly it does not belong to the null space of A and left null space, because null space means what? That it means it needs to be a zero eigenvalue. So it is not a non-zero eigenvalue. So it does not similarly for left null space also, because the transpose and A matrix share the same eigenvalues. So it will be it can only be zero, then only it can be belongs to the left null space also. Right. So okay, now this question, yeah, this is what
Excuse me.
yeah.
Uh, the way you solved it, and we
Hmm.
found some coefficients A, B, C, which,
Right.
if we use A, B, C to combine the rows of A, we'll
Hmm.
be able to get exactly the eigenvector that
Eigenvector.
we had
Right.
calculated.
Right.
So one part of me was thinking in terms of domain and range, and
Hmm.
clearly the eigenvector is multiplied on both sides of that, right? We transform the eigenvector in the domain, and then we also see it in the range side. So by that logic, we should be able to conclude the same thing. Is that correct?
No, you are able to see vector in both domain and range, because it is a map from T3 to the vector is in R3. So domain and range both are R3. That's why you're able to see the vector in both. But that doesn't lead you to anything.
Like the row space is making up my domain, and the column space is making up my range.
No, row space does not always make your domain. You can have a matrix with row rank not equal to 3, but you can have, the domain is R3. So the dimension of domain is 3 dimension, whereas your matrix may have a row rank not equal to 3, right? Not every matrix is invertible, but in this case, that is true because you have an invertible matrix. In this case, you can think of it like that, but not always. Do you see my point?
Right. In this case, we have an operator, and the matrix
No.
is also invertible. So
Yes. No, the matrix is invertible. That's why you can think of that because it is invertible, so it has full rank, right? It does not have nullity. So because it has full rank, uh, the domain is generated by 3 vectors. Okay, three domain is R3, so it can be any 3 linear independent vectors will generate this. So that's why because and these 3 vectors are independent because it has rank, it has full rank. So then you can think of. But whatever you are saying, that is not true for that is not true in generality. You need to have invertible matrix operator. So yeah, so whatever you said is correct. You are on the right track, but it needs some hypothesis to start. You cannot just have any matrix. Right. Yeah. So that is exactly what I did. Yeah, precisely. If you want to think, uh, yeah. So yeah, that's a good takeaway. If the matrix has determinant non-zero, then you can quickly say that the eigenvector will belong to the row space. And if the determinant is 0, then you cannot say that it will be belong to. But then it may also belongs to the row space uh, because yeah, it will always belong to the row space, right? Unless yes, so it will always belong to the row space.
Excuse me, sir.
Yeah.
Sir, if the in this question, if eigenvector is belonging to the row space, then how AV is equals to lambda is satisfied? There, then there will be not multiplication, right? Multiplication is not possible.
But
The expression AV is equals to lambda V, sir. The row space is consist of the vectors in rows, right? And the
right.
eigenvectors are the column vectors. So how the column vector and the row vector in this way is equal?
No, it's not like that. You can think of row space also. What is a row space? Row space is R3 in this case, right? It is uh, generated by the row vectors. Vectors are in R3, so it will always be the generating set,
But
right?
the vectors are in row vectors, right?
That doesn't
And
matter. That doesn't matter.
it doesn't matter.
Yeah, it doesn't matter.
Okay.
As long as they are in the same vector, they represent the same vector in R3, it doesn't matter. Yeah, so okay, so yeah, there is a takeaway like this that it will always belong to the row space because if it does not belong to the row space, then it will be in the null space of the operator. But null space is always occupied by the eigenvectors corresponding to 0 eigenvalue. So if there is a non-zero value, that means that vector has to be in that vector has to be not in the null space. That means it should be in the row space. Okay. Yeah. Right. So that is good. Right. So let I can remove this all calculation. Yeah. So what I'm saying is that so you have a so what is a row space in particular? So row space is set of all vectors in R3. Uh, yeah. Such that AV. Yeah. Yes. So 0 can also be null spaces and 0 space can also be there. That is true. But if I look at vectors, mm, yeah, so it is basically R1, the span of the rows, Ri. All right. Now what is this? Span of rows, Ri. Now what is this? So this in particular consists of So what will be the basis of this? The basis would be the independent rows. Okay, so linearly independent rows. Right. And then there will be the dependent rows will correspond to the zero, will correspond to the null space. So we will not be worried about that. So if there is a vector, eigenvector corresponding to the eigenvalue 0, eigenvalue 1, some non-zero eigenvalue, then it cannot be in the null space. It has to be in the row space. So that is the argument. So then it has to be independent. It has to be combination of these independent rows. So the proof that I just wrote earlier was kind of a proof and whatever we discussed. So what Tanzil mentioned is actually making sense. You don't need invertibility in order to say that. Yeah, it will always be belonging to the row space of A. And column space, I just gave the argument how to see it is in the column space. And this is happening because you are looking at the operator which is T3 from F3 to F3. So yeah, we are looking at the operator. That's why it is true. Matrix representing the operators. All right. Right. Is that fine with everyone?
Yes.
Yes, sir.
Okay, good. So now, yeah, so I will give you another couple of minutes to think about this question and then you may answer.
Well, one of the answers, okay, you just marked the others as well. Fine. It's just A and C, right?
Yeah, the A and C are the correct ones. Okay, how to see them? So A and A transpose have the same eigenvalue. That means what? So if you look at, so what are the eigenvalue? Eigenvalue are the roots of this polynomial. Okay, A minus lambda I. If you transpose this matrix, so we know that determinant is preserved under the transpose. So if you transpose this, then you will get the same determinant. Right? That means the root will be the same. And what is the transpose of this matrix? So transpose of A minus lambda I transpose is nothing but A transpose minus lambda I transpose, which is A transpose minus lambda I. All right. So this will be the same as determinant of A transpose minus lambda I. So the roots of the polynomial, because the polynomial is same, the roots will be same, so eigenvalues will be same. So that's why A is correct. They can have a different eigenvectors, so B is not correct.
So, if we have same eigenvalues, so how the eigenvector will be different?
Yeah, eigenvector will be different because the matrix is different. Two matrices can have same eigenvalues, but they need not to have the same eigenvector.
Okay, sir. Okay, sir.
Right? So A and A inverse have the same eigenvalues. Is
Uh,
no,
Eigenvalues is
1 over
proportional.
lambda. Yes, the inverse of the reciprocal of the
Yes, yes.
eigenvalue. And but the eigenvector will be the same. Same. Okay. So for example, if you have lambda v is equal to av is equal to lambda v, that means if you multiply a inverse both sides, so what will you get? You will get this will be 0. So 1 over lambda v is equal to lambda inverse v. Okay, so the eigenvector remains same. The eigenvalue change to 1 over lambda and so on. Now my question to you is that suppose A is invertible matrix, then uh, then uh, 0 be an eigenvalue of A. Can 0 be an eigenvalue of A if A is invertible?
No, sir, because it is invertible.
Yes, that is true. So if suppose if 0 is an eigenvalue, that means it will have some nullity. Okay, that means there is some non-zero vector that lies in the kernel, that lies in the null space of A, which means that the determinant has to be zero, which is a contradiction to the inverter. Good. All right. So now we have talked about the eigenvalues, eigenvectors, AM, algebraic multiplicity, geometric multiplicity. We have revised all these things. Now let's look at the condition. So we have seen this condition that GM of an eigenvalue has to be smaller than the algebraic
Excuse me, sir.
multiplicity. Yeah.
I didn't get the third option. I think it is not the right. The A and A inverse have the same eigenvectors. Sometimes they will, but not every eigenvector of A inverse is the same as the eigenvector of A. So how it will be same?
No, no. Look, this is the proof. Look at this. Suppose you have this lambda is the eigenvalue and corresponding eigenvector is V. You just multiply A inverse both times. Okay, so you will get A inverse B is equal to 1 over lambda B. So the for lambda 1 over lambda, the eigenvector is same V, which was there for lambda. That's the proof. So the eigenvector remains same. Okay, so AM, we know this relation that AM lambda is smaller than equal to GM lambda is smaller than equal to AM lambda. All right. Now what happens when the equality holds true? So if the equality holds true, then you can diagonalize your operator. Okay, what does it mean by diagonalizing an operator? That means you can find out a basis with respect to which the presentation, the matrix representation of T is a diagonal matrix. Okay, then there exists uh, a basis of Fn such that the matrix representation of T from Fn to Fn is a diagonal matrix. Okay, so this is what called the diagonalizability, and diagonalizability holds true when the eigenvalues, the algebraic multiplicity and geometric multiplicity are equal. Okay, so all right. So let's take an example. Okay, so consider the following matrices. Which of the following are diagonalizable? So it is easy to check. For each of the matrix, you need to calculate the eigenvalues and calculate their respective geometric and algebraic multiplicities. And if they are equal, then you know they are diagonalizable. All right. So the first matrix A, the eigenvalues are. So let me take a table A, B, C, D. So the eigenvalues for A are 2, 2, 3. All right. Similarly, for B, it is 4, 5, 6. They are all simple matrices. For D, it is 1, 1, 1. Now, what about for C?
It looks like one will be there twice.
So you can calculate the eigenvalue for C. So let's not go into that. Okay, so now let's look at matrix A. So is A a diagonalizable matrix?
Yes, I think because the geometric multiplicity would be 2.
Geometric multiplicity would be 2. Okay. So algebraic multiplicity of 2 is 2. Uh, Now, my claim is geometric multiplicity of 2 is 1. It's not 2. So it is not diagonalizable. So let's check that. So let's check whether I'm wrong or right. So if you look at this matrix, it would be 0, 1, 0, 0, 1, 0, 0, 0, 0, 0, 3. Clearly, you can see there is only one independent vector, independent variable, which is x. So what's the nullity? It is 1. So what's the geometric multiplicity? It is 1. All right.
So can't we say that one vector would be 1, 0, 0, and another vector we can find from a minus 2I?
It is 1. Yeah, so 1, 0, 0 is the only vector that is that's in the null space. What's the other vector? With this calculation also, you will find out 1, 0, 0 is the only is the generating of this null space. Right? So nullity is 1. That's all you need to find out. There is no other way.
Okay, sir.
Yeah. Okay, what about B matrix? Matrix B. Because all three are independent, disjoint eigenvalues, so their geometric and algebraic multiplicity will be equal to 1, and it is already given in the diagonal form, so you don't need to diagonalize it. All right. So this is so matrix A is not diagonalizable. This is already diagonalizable. What about C? You can. This is an exercise for you. You can think about it, and then uh, what about matrix D? Is it diagonalizable? Is it not diagonalizable? The algebraic multiplicity of 1 is 3. But what about the geometric multiplicity? So
By
this
the
is,
same way you have solved for A, I think we'll get geometric multiplicity equal to 1.
yes. So that means it is not diagonalizable. All right. So only B matrix is diagonalizable. We don't know about C. So C must also be diagonalizable. I don't know whether it is diagonalizable or not. So that's an exercise for you to see. Okay. Now let me um, all right. Let's skip this for a minute. Yeah. Which of the following matrices are diagonalizable? So again, you have three matrices. Is A diagonalizable?
No,
Why?
because we will have geometric multiplicity 1 when the
For which eigenvalue?
I think for 2 and 3 both.
No. For 3, we will have geometric multiplicity equal to 2. But for 2, we will have geometric multiplicity equal to 1.
Yes, sir.
Okay. What about case B? So this is not diagonalizable, as geometric multiplicity of 2 is 1, algebraic multiplicity of 2 is 2, geometric multiplicity of 3 is 2, which is equal to algebraic multiplicity. All right. What about matrix B?
Not diagonalizable.
Again, by the same logic, right? So it is not. What about matrix C? Yes, Sonali.
So how do we find the geometric multiplicity here?
Which case?
So in first case,
Yeah, how do we find usually? So that's just follow that. So for geometric multiplicity of 2, this is A minus 2I, right? For geometric multiplicity of 2, we need to find out the dimension of this nullity, right? This has to be equal to algebraic multiplicity or not. So what is this A minus 2I? Tell me.
It's 0100,
0100.
000,
Yes.
and then 0010, and the last one is the 0001.
Right. Now, what is the null space of this matrix? Or in particular, you just calculate. If you want to calculate the nullity or dimension of the null space, so just calculate, just count the number of dependent and independent variables. So, how many independent variables are there? That will be your nullity.
Okay, sir, understood.
Yeah, how many independent are there? You can complete the argument.
Here, one.
One, right? So that will be your nullity. So that's your geometric multiplicity. Okay. So you can do this calculation. This is not hard. Okay. Now what about C? Is C diagonalizable or it's not diagonalizable?
No, sir.
Is it diagonalizable?
Not
Not
diagonalizable.
diagonalizable.
All right. So it is also not diagonalizable. Okay. So these are not diagonalizable matrices. Okay. So when we have a diagonalizable matrices, so then what we can do, we can find out a basis with respect to which we can calculate, we can represent our matrix or our operator by a diagonal matrix. Okay. So there is a change of basis that we need to perform. So let's look at this. Right. Suppose, yeah. Suppose you have, so we want to find out the coordinates of a vector with respect to a different basis. All right. Suppose you have a vector given with respect to canonical basis. Usually, we write vectors in a canonical with respect to canonical basis. Okay, so you will have this presentation, this vector coordinates given, which simply means that x v is nothing but x1 e1 plus x2 e2 up to xn e. All right. Now we choose a different set of bases, which is u1 to u1. Now each u1 to un is u1 to un is a different set of bases, but you can express u1 to un with respect to the canonical basis. Okay, because any vector can be expressed with respect to a given basis. So you can express u1 to un with respect to the canonical basis, and it will have some coordinates like this. Okay, so this is how you can express it. Now suppose you have same vector v given with respect to the new basis u1 to un. Okay, that means the coordinates x1 to x1 x1 prime to xn prime are given with respect to the basis u1 to un. All right. In other words, you can express v is equal to like this. Now the question is, how can you obtain coordinates of coordinates of vector u v with respect to the canonical basis if you are given basis with respect to the new basis, the coordinates with respect to the new basis. So the idea here is that you need to perform a change of basis. You need to multiply your coordinate vector with a change of basis matrix. So this change of basis matrix basically converts your basis coordinates from V to EIs, VIs to EIs. Okay, sorry, in this case it is UIs to VIs. It converts your basis to UIs to VI. Now, what is this UI to EI matrix look like? Each of the column is expressing UI in terms of EI. Okay, so that you need to keep in mind. If you want to convert a coordinate of vectors from one, if you want to convert a vector, vector coordinates from one basis to another basis. Okay, suppose you want to convert from basis UIs to basis EIs, then okay, then you need to express each of the basis UI in with respect to basis EIs. Okay, and whatever the expression, whatever coefficient that expression has with respect for each basis vector, that will become the first column. That is what happens here. So you express u1 with respect to e1 to en, and the coefficients become the first column, and so on. Okay. And the other way around, if you want to convert from ei to ui, you just take the inverse of this change of basis matrix. You will get ei to ui. So in my notes, in my live session, I denoted this matrix with P. Okay. So you can also have the same denotation. All right. All right. So now let's look at this question. Okay. So this question is a bit different from what we did in the live session. So that's why I want to emphasize on this. Suppose you have suppose you have two bases where first one basis is u1, u2, u3. Another basis is v1, v2, v3. Okay. So u is equal to, u is a vector which has coordinate a, b, c with respect to basis u1, u2, u3. Okay. And d, e, f are the coordinates of the same vector v with respect to another basis v1, v2, v3. Now P is the matrix that converts. P is a change of basis matrix. So it converts uh, it converts u into v. Okay, it takes coordinates with respect to u and gives you the coordinates with respect to v. All right. So now, which of the following option represents the matrix P correctly? So let's see this. So we noticed in the previous part, if you want to convert, yeah. So in the previous part, we have seen that if you want to convert, if you are converting your coordinates from ui to ei, then you need to express each of the ui with respect to ei. Okay. Same thing we will do here. In this case, we want to convert matrix P. We want to convert ui's into vi's. So what we need to do? We need to express each of the ui with respect to vi, and that will become our column. Okay. So let's do that. So what is u1? u1 is 3, 0, 3 minus 1. You need to express it with respect to vi. Okay. So 3, 1, 2. So that will become your first column. So let me write with that a1, 2, 1, a3, 1. What is a21? 5, 0, 1, 4, 1, 1. Now let's solve this. So first equation says that 3, 5, 4, sorry, yeah, 3, 5, 4,
1 0.
and then is equal to 0, and then 1, 0, 1 is equal to 3. So I'm writing the augmented matrix because this corresponds to a linear system equation. I can write down to solve this in terms of a11, a21, a31. I can write down the augmented matrix. All right. Right. The third row is 2, 1, 1 equal to 1. Right. So this is your matrix. Now let's solve this matrix. The first operation that I can do is divide R1 by 3. I will get 1, 5 by 3, 4 by 3, 0, 1, 0, 1, 3, 2, 1, 1, minus 1. All right. Now, what I will do, subtract R2 minus R1, R3 minus 2R1, 1, 5 by 3, 4 by 3, 0, 0, minus 5 by 3, 1 minus 4 by 3, 1 minus 4 by 3, this will be, and then 3 minus 0, So it will be 3. So this will be minus 1 by 3. And then 0. 1 minus 10 by 3. 1 minus 8 by 3. Minus 1, 0. So it will be 0. Alright. So what is this? This is 3 minus 10. Okay, 3 minus 10, minus 7 by 3. This is minus 5 by 3. Alright. Now this is what you have obtained. Now what you can do, yes. So now, yeah, we divide R2 by 3 by 5 minus 3 by 5. We will get 1, 5 by 3, 4 by 3, 0, 0, 1.
So we can also do R1 is equals to R1 plus R2.
Yeah, you can do that, but okay, that will simplify things. So R1 plus R2, let's do that. So you will get 0 over here, and then you will get 1, and then you will get 3 here, right? And then 5 by 3 minus 1 by 3, and then you what 5 by 3, 1 by 3, 3, 0 minus 7 by 3,
So
1.
minus 1 by 3.
Right. So now we will do R2 by minus 3 by 5, and yeah, let's just do that. So you'll get 3 minus 9 by 5 minus 1, 1, 0, 1. First row remains as it is. Second row becomes 0, 1, 3, 3 cancels out, and it will be just 5. So it will be 5. Third row, I'm writing it as like this. So no problem with that. I've just multiplied third row by R3 times 3. So we'll get this. Now R3 plus this, you'll get
Sir,
0.
at the position to row 2 3, it will be 1 by 5, right? After you have doing the operation minus 3 R2 divided by 5, it will be here 1 by
Oh,
5.
right. Right. Um, yes. Yes. So now what we're doing? So now we are adding up things. So R3 plus 7 R1 minus 5 plus 7 R1.
Sir, you are doing R3 plus 7 R1, but here in the
Sorry,
2
R2.
it is 0. Acha,
Sorry,
R2.
sorry,
Then
R2. And minus 3 plus 21 by 5. What? Sorry. It would be 27 by 5 and minus. All right. Yes. So then it is from 0, 1, 3, 0, 1, 1 by 5, minus 9 by 5, 0, 0, 1. And then it will be, what is this? Minus 25 plus 7, minus 18 by 5. And here it would be minus 15 plus 27. minus 15 plus 27, that is 20, 32, 42 minus 52 by 5. Okay, this looks all right. So now we can do the rest of the calculations. R2 minus R1, R2 minus 1 by 5, R3, right? And R2 minus, okay, this is becoming computationally hard. Okay, so too much competition, and I don't think none of the option matches with this, right? Or does it? Okay, we can still this 6. This will be what 1 times 4. Yeah, we can still divide this. We can divide by 6. 3. This will be 7. 3 by 7. Do we have something like this? Nope. Don't have anything like that. Okay. All right. Anyway, let's finish up this calculation and then let's see whether we get the correct answer or not, or maybe the options given are wrong. So either of the cases. Okay, so let me subtract this because this is 7 by 3 only. Okay, this is minus 9 by 5 minus 7 by 3 times 5. So I can take 1 by 5 out. Right, and then this will be um, minus 27 minus 7 minus 34. Okay, and then this is 7 by 3. All right, so it is not matching with the calculation that so this is 3, this is 4 by this is 4 by 6, which can further be it is 2 by 3. All right, so what do we get is A11 is 2 by 3, A21 is minus 34 by 15, A31 is 7 by 3. Okay. So the first column should be this 2 by 3 minus 13 by 5, 15, 7 by 30. And the second column and the third column is yet to calculate. Okay, so this is how we can solve this. Anyway, none of the option is matching, but you got the idea how to find out this matrix, change of basis matrix. That was the point.
Excuse me.
Yeah.
Is there no better way of doing this?
No. So it usually becomes simpler when you have canonical basis on one end. Okay, then it becomes simpler because you just need to express the. Suppose if you have canonical basis on the left hand side, you want to convert something to canonical basis, right? Then UIs are already given with respect to canonical basis, so your column will become UIs, U1, U2, U3. That is what happens when we have diagonalizable case. Okay, when you want to write down the matrix representation in terms of a diagonal matrix. Okay, that is what happens. So in that case, this calculation will not come. Okay, while diagonalization, when you want to write down operators diagonal form, and this calculation will not come. You just need to calculate P and P inverse matrix, and then appropriately you can multiply and you can get the option. This is like an extra exercise to make you comfortable with the topic, but it looks like the calculations itself either this one of the option is wrong or of the all the options are wrong, because if you take any of the option you will not get 0 1 0 3 minus 1 on the left hand side. So I think this is options are wrong. Okay.
I was thinking
All right.
about it like this. See,
Hmm.
if I want to go from, let us say I want to go from UI basis to canonical
Right.
basis, then I will build up my matrix with the columns of U. So U1
Yes.
will become first column, second column will be U2, U3, and then I will invert that matrix. That will
Hmm.
take me from canonical
Even
to
EI
UI.
to UI. Yes.
It will take me from EI to UI, that basis. Okay, now I am in UI. Now I will multiply it with my P matrix, right? P
Yeah.
is acting on U. P is acting on the U basis
Right.
matrix,
Right.
and it is taking me to V. So now I will
Yes.
hit this U inverse with P. Now I am
Right.
in V after the P operation. Now
So
I
you
am
have this matrix, and then you similarly calculate this matrix, right? Now you want to, so let's call that to be R. Now you want to club this. So you want to start with coordinates with UIs, right? That's what we are starting with.
no,
And
I
then,
start with EI. I start with EI. I go to
no, you
UI
can do,
using U
so
inverse.
whatever you're saying is correct actually. You can do this, you can take this. So this will give you this matrix, this should give you the matrix P. Because you start with UI in this, you get EI, and then on EI you can apply this R inverse and then you can obtain VI. Yeah, that is simpler. That is what we want, right? We want a matrix
Uh,
Q which takes me UI to VI.
so can we please try this approach? Let us see
Yeah,
if
yeah,
it
yeah.
gives
So
us similar.
that's a good way. Okay, but I still need to calculate R inverse of that matrix. So what is the first matrix? This will be your 0 3 minus 1 minus 2 0 1 minus 1 0 1, and R is VI to EI, which will be 312 501 41. So all right. So we need to find out R inverse. So R inverse will give you this. So what is R inverse? So first three cofactor matrix and then transpose of that divided by the determinant. So first calculate the determinant of this matrix. Determinant of this expanding along this line, you will get 5 minus 4 1 minus 1, and then 3 minus 10 minus 7 plus 7 plus 7 minus 1 6. Right, that's why we are getting 6. Right. Okay, now the adjoint, the cofactor matrix. So that means 3 cofactor of 3 is minus 1. Cofactor of 5 is 1 minus 2. Minus 1 plus 1 4 1 0. For 2 1 it is 5 minus 4 minus 1. It is 3 3 minus 8. 3 minus 8, that's minus 5. And then my 3 minus 10, that's minus 7. And then 5, then 3 minus 4 1 minus 5. Okay, so now let's multiply them. So this, now we need to take transpose of this, sorry. So 1 over 6 transpose of this matrix will be minus 1 1 1 minus 1 minus 5 minus 5 1 minus 5. Right, okay, so now this matrix times P. So minus 1 0 minus 3 minus 5 minus 8. Minus 15 minus 16. Then minus 2 plus 1 minus 1 minus 1 plus 1 21 plus 5 26. Okay, we are getting the same matrix. So now minus 2 minus 5. This will be 1 minus 1 minus 6. Right. Yeah, we get the same matrix. This is much simpler. Thanks. Yeah, but I don't know why this, the method that I was using earlier, does not give me the correct answer. It should also give me the correct answer. But anyway, yeah. So by our calculation, it seems like B is the correct option. Yeah, this is much simpler.
So, can you write in one page that the formula of changing UI to EI and changing EI to UI?
Just a second. Yes. So yeah. So this is the formula. So you want to convert. You want to find out a matrix which is from P should be from. You want to find out a P which is from UI to VI. Right. So as Tanzil mentioned that you can break this into two parts. First is to UI to EI and then VI to EI. Okay, because these are simpler matrices to write down. And then because you want to go from UI to VI, so you will first go to UI to EI and then from EI to VI. So for EI to VI, you need to find out the inverse of this matrix. So that's what I did. And then you will get, and then you multiply these two matrices. So you will get the answer.
Yes, sir. But I meant the general formula. Can you write it?
Yeah, this is general formula only, right? This till this point in this description, I'm not mentioning anything that is this 3 cross 3 or something like this. So this is general formula,
Okay.
right? Okay, so let's right. So yeah, so what will be the answer to this question? Can anyone tell me? So what should we do first of all? Not right away.
First, we will find the eigenvectors and write the diagonal matrix. Then we can write
Right.
this matrix.
Yes. So that is correct. So we will first find out the eigenvector. So if you look at a square of this, let's say, then the thing is that this will go away in some point. So if this will go away, it will become then this diagonal matrix. So just try to see what happens at these two entries. So it will be this square. The diagonal entries will be the square ones, not change. Look at this. Look at this entry. So what happens to this entry? So it will be 0 again. This entry will get multiplied to this. Sorry. So this entry we will multiply to the third column. So it has this thing. So it will be 0.202. Right. And this entry, which is on the second column, fourth entry,
So can we just simply say that when we will make this thing as a diagonal matrix, so because 0 0.1, 0 0.2, 0.3, they all are less than 1, so it will go to 0. Means we will get 0 matrix in between, so the whole thing will become 0.
Yes, that is true. That you will get. So this the answer to this question will be the zero matrix. That is true. That your intuition is correct. If you can argue that, that is completely okay. I'm just trying to think that whether this will go away or not. Looks like not, because this what will be the entry here? It is two second row, fourth column. Second row, fourth column. That means second row will get multiplied with the fourth column, so it will be 0.03. Okay, it will stay. Yeah. Okay, so yeah, so the other way is to find out the diagonal entries, and then uh, yeah, the the eigenvalues are simple. The eigenvalues are the diagonals. Diagonal entries are the eigenvalues, and then for diagonal, in order to say it is diagonalizable or not, you just need to find out. So it is this. These are the two with the same geometric algebra multiplicity. You need to check for point two. So if you subtract point two, what will you get? So if you subtract point two, you will get that this will be 0 and this will be 0, this will be minus zero point 0.1 and this will be plus 0.1, and then you see that this is this and this is 0, this is 0, so it will have, yeah, yeah, the nullity will be 1, so it is not diagonalizable, right? It is not diagonalizable, right? So you need to come up with a different approach. You need to calculate the inverses, and then you need to find you sorry you need to calculate the square, you need to calculate the power, and then you need to find out the pattern. That is what I was thinking. Okay, so it is not diagonalizable. That is clear, right? This matrix is not diagonalizable if you try to do it.
Excuse me.
Yeah.
I have a feeling it is diagonalizable.
Is it?
The reason being the point twos will take each other out. So the second column will be all zeros, and the third column and first column are multiples of each other. So nullity is still 2 only.
Yeah, that is true. So it will be 0.1, 0, 0, 0, 0.1, 0, 0, 0, 0, 1, 0, 0, minus, sorry, it will be this minus, and then this is this. Yeah, nullity is 2. Yeah, what I was saying, I was wrong. Nullity is 2 because, right, this is multiple of this. This is one independent variable. So this will go away. Multiply x, y, z, w to that. You will get x plus z equal to 0. And then you will also get z equal to your z can be anything. Your w is 0. And your y can also be anything. Yeah, there are two rows which are 0. So yes, it has nullity equal. Right. So right. So that is true. So you can do diagonalizable. So it is diagonalizable. Thanks. Okay. Last part of the discussion is the circulant
Excuse
matrices.
me.
Yeah.
One more thing here. Do we really need to build up all the eigenvectors? I mean, once we say a matrix is diagonalizable, then it
Huh.
goes P, D, P inverse. And if D itself, the eigenvalue containing matrix, diagonal matrix D, if that itself is going to 0, then it doesn't matter what
Yeah,
P
yeah,
and
yeah.
P inverse
Yeah,
are.
yeah. So you are correct. So you can just say that because it is diagonalizable, you can find out a matrix P, change of basis, so that you can write A to B P D P inverse, where D is just the diagonal matrix 0.1, 0.2, 0.2, 0.3, right? Rest is 0. And then if you take the power here, then it will be just P D N this, which is the power at the diagonal entries, and that goes to 0 as n tends to 0, as n tends to infinity. So this is fine. So you will get 0 matrix in the between, and then this as n tends to infinity, which will give you 0. So that is fine. That is a completely paradigm. You don't need to calculate P matrix. Okay, so suppose you have this matrix A, you want to find out the eigenvalues. Now, this is a circular matrix because the columns are in the circular motion to one another. So you will get, so what will be the eigenvalues is, so we know the formula. So for eigenvalue, because in this case, there are three entries. So C naught is 3, C1 is 2, C2 is 1. So the first eigenvalue will be the sum of all these three things. So that will be 6. 6 is an eigenvalue. We need to find out the other two eigenvalues. So other two eigenvalues will be this. Right. So we need to take j is equal to -1. So lambda 1 will be C naught plus C1 omega to the power -1 plus C2 omega to the power. Okay, so what is omega inverse? Omega inverse, you can multiply omega cube to it, you will get omega square. So omega inverse is nothing but omega square. Similarly, omega -2 is equal to omega. All right, so what will you get? You will get C naught plus C1 omega square uh, C2 omega. All right, so now what is omega? Omega is 2 pi by 2 pi I by 2 pi I by 3 in this case, because n is equal to 3. N is equal to 2 in this case. So it is, yeah, because we are considering 0, 1, 2. So that's why it is n equal to 2. It should be
Should be 3 only,
3.
I
It should
think.
be 3. There is some problem with this. Oh, we are okay. Okay. Right. We are going up to n minus 1. Right. So it is 3. 2 pi by 3. Okay. So you can calculate the second eigenvalue as well. So lambda 2 would be C naught plus C1 omega to the power -2 plus C2 omega to the power -4. Again, what is omega -2? It is omega only. What is omega -4? It is omega, but get multiplied with omega to power 3. You will get -1. Omega -1 is omega square, so it will be omega square. All right. So this will be the omega 2. All right. So yeah. Okay. So let's. So what is lambda 1 then? Lambda 1 is C naught. C naught is 3 plus 2 times omega square. So that means e to the power 2 pi I to the power 4 pi I. plus C2, which is 1 times e to the power 2 pi I by 3. So calculate them, you will get this is 2. What is this? Is cos 4 pi I by 3 plus I sine 4 pi I by 3. You can break this into, there is no I in it. This is cos pi plus pi by 3. This is sine pi plus pi by 3. So what is cos pi plus pi by 3? It is cos pi by 3.
Minus cos pi by 3, I think.
Yes, sir. Minus, I guess.
Yeah, it is minus because it's on the third quadrant. It's minus cos pi by 3. And what about the sign? It will again be minus sine pi by 3, right?
Yes.
Because it's in the third quadrant. Third quadrant is tan, and tan is positive. First and third. Cos is in first and fourth. Makes sense. Okay. 2, 3. And then this similarly you can calculate. This is 2 pi by 3, which is like 120 degree. Cos 120 degree is it is 1 by 2 minus 1 by 2.
Negative.
Minus 1 by 2 plus I, this is 3 by 2. And if you calculate this cos pi by 3, what is cos pi by 3? 1 by 3.
Minus
1 by 2. No, it is just 1 by 2. So just do 1 by 2. This will be just 3 by 2. I will be here. 2 will cancel out. Let's keep the 2. So it is 3 minus 1. So it is 2. 2 minus half. 2 minus half, it is plus I times this and this factor. So root 3 by 2 will come out. So it is 2 times 2I, 2 plus 1. 2 minus 2, so it is minus 1. So it should be 3 minus root 3 by 2. Is that even an option? Yeah. Sorry, I is also here. So the option D is correct. Right. 3 minus root 3 by 2. That's lambda 1. Similarly, you can calculate lambda 2. So I'm not doing that computation. And you can find out which
So that
is
will be
the.
conjugate of it, I guess.
Sorry?
That will be conjugate of it, right?
Yeah, that will be conjugate. Yeah, that should be conjugate of this. That's true. Right. Because the root of polynomial, so it should be conjugate of this. So none of the other options are correct. Right. So A and D are the correct options. Okay. It's a repetition of the same question. Oh, all right. So yeah. So till this point we had to discuss. So Tanjil, coming back to your doubt, which you asked me in the live session. So you asked me about the trick that professor used to calculate the near diagonal form, right? How to find out that basis.
Right,
So
that extra vector.
Yeah, the extra vector, right? So let me, yeah. So let's take, for an example, yeah, let's take this thing. So what you want to do is you want to find out a vector A. You have already v1, v2. V1, v2 are coming from the eigenvectors. They are eigenvectors for some lambda 1, lambda 2. This is ABC, that is the new vector that you are adding. And your A is C1, C2, C3, right? Similarly, yeah, so you will be having like this. So diagonal form here and then this. So I have written down the first, so the near diagonal form, because other twos are the eigenvalues, correspond to eigenvalues. So they will be just in the 1, 0, 1, 0, 0, 0, 1 type. Now this one cannot be in 1, 0, 0, 0 type because ABC is not an eigenvector. Okay. So let's take what's the simplest form. So this seems the simplest form, 1, 1, 0. Okay, this should be the simplest choice of the vector we can have in the diagonal near diagonal matrix. Okay, so this is your near diagonal matrix detail. All right. So now this is the setup. Now you want to find out ABC, right? Such that this you will get this D as a representation of the operator. So now let's try to solve this. So it is A plus C1. So what is the first column? First column, we will compare the first column only because that first column will have ABC in it. So let's compare the first column from both of the multiplication. So first column here will be A times C1, B times C2, C times C3. Second, first column here would be in the multiplication, it would be 1 times ABC, 1 times B1, right? Just recall the matrix multiplication. So that would be the case. Now, I already know what is V1 and I want to solve this type of equation. I want to find out appropriate ABC so that I will get the solution. So now you compare these two matrices. We know C1, C2, C3, we know V1. We need to compare these two so that I will get some appropriate solution. So in the particular example that professor takes, in that example, it turns out to be that uh, you will get these equations, right? A plus B is equal to, so first equation is A is equal to A. Second equation is A plus B is equal to B minus 2. Third equation is A plus B plus C is equal to this. So A is equal to A doesn't give you anything. Second equation gives you about what can be your A. Okay, because B cancels out. So what can be? So A has to be minus 2. Now if you take A to be minus 2, B and C are independent in some sense. Okay, they can be anything which satisfies this equation. So you can take C to be 0 for your convenience. You take C to be 0, then you can find out B in terms of A. Okay. Right. So yeah, so then you can have A and B such that your matrix will have the diagonal matrix will have this the near diagonal form will have 1 1 here. So that's one way that I can think of to find out appropriate basis so that you will have this thing.
Okay, you mind if I ask a question?
Yeah, please.
Here we the actual diagonal form itself will be, I mean, near diagonal form will be SDS inverse. We are just writing it in a way that the S inverse
Yeah,
is on
this
the
will be
other
the
side.
diagonal. This will be the near diagonal
Right, right.
matrix.
Okay. This first equation you have written here,
Hmm.
A C1 plus B C2 plus C C3. This
Hmm.
is just going to give us the first column, that is ABC
Yes.
itself, right?
Yes. Yes. Yes.
But there's a
Not
plus.
the ABC. Not the ABC. The one which you will get by multiplying over here.
Okay, that one. Okay.
Right. So that will be the multiplication first. What it would be? It would be 1 times ABC and 1 times B1 plus 1 times B1. So this is what we will get.
Oh, that thing. Okay. And we know that the V1 will always multiply it in the second position, because that is how V1 is designed. The eigenvector V1 will
Right.
only multiply the second element over there.
Yes, 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 yes.
I mean, it has to multiply the vector 0, 1, 0, because that is how everything is set up.
Yes, 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 yes.
So we pull them apart with that logic. We
Yes,
pull
yes.
apart 1, 1, 0 as 1, 0, 0 and 0, 1, 0.
Yes.
And then we say that 1, 0, 0 can only multiply ABC, because the other two are 0. So V1, 0, V2, 0, and then the other one goes to V1, and that's how we
Right.
arrange this up.
Yes. And then you find that you can make appropriate choices for C because you get this equation. So anything which satisfies C, B, you can have appropriate choices. You can take C to be 0 or B to be 0, let's say. Then you can have the answer.
Okay, thank you. Very nice to see. Thank you.
Yeah. All right. So we end our today's discussion at this point. I hope we don't have any further questions and doubt, and I hope I made a few things clear, and then you might get some idea also about a few things. I will share these notes as usual. So okay, all the best for your quiz, and then we will see you next week. All right. Bye everyone.
Thank you, sir.
Yeah.
Thank you.
Thanks. Thanks for joining, guys. Yeah.
Thank you, sir.